Thank you, Usman. You can come in. All right, so let me welcome Josh Engelsma. So I met with Josh probably last year for a big moment. So Josh did his, Josh is actually GVC alumni. I think you graduated in 2013. 2016, okay. So Josh graduated from GVSU at 2016. Then he did his PhD under Oliver Jane at MSU. And Josh's PhD focus was actually fingerprinting. So I don't know a lot about his PhD thesis. He's going to talk about this, but I'm going to talk about rank-on computing a little bit. Sure. And if that's okay. Yeah. So rank-on computing is a company based off of Colorado. They work with fingerprinting and biometric stuff, right? And if I remember correctly, in December, you guys won one competition on fingerprinting. And in January, you won another competition on facial detection.
That's right.
That's right. And that's number one, by the way. That's the first US-based company based on fingerprinting and facial detection across the board. And I think you beat the nearest competitors by the orders of magnitude in terms of accuracy, in terms of efficiency.
In terms of, yeah, efficiency specifically and accuracy, yeah, I wouldn't say orders of magnitude.
Orders, yeah, of course, yeah. But efficiency, yeah, I think it was 1,000 times or something.
Yes, efficiency, yeah. Yes.
Efficiency, yeah. So this is very exciting times. So that means they're going to get bigger. And Jot is based on Grand Rapids. So if they're getting bigger, here it's Southern Rapids and Grand Rapids is going to get bigger too. So students, go network with him. With that, thank you, Josh, for being here. Thank you so much. And I'm going to hand over my page to you. So you can just
Does this work good? Okay. Yeah. Thank you, Rahat, very much for that introduction. Still feels more quiet. Is this a little better? Try that. Thank you, Rahat, very much for that introduction. Thank you all for being here. I'm very grateful for this opportunity. Very thankful to be here. As Rahat said, I started my computer science journey here at Grand Valley State, doing my undergrad in computer science. I see many of my former professors here, and I'm very grateful to each one of them for their role in teaching me, mentoring me, and preparing me for a lot of the work that I'm going to be presenting on today. Also see my former high school robotics coach here today, showing support, so I'm also grateful for that. As a quick show of hands, I thought it'd be good to just get a feel for my audience. How many people here today are undergrads? So we have quite a number of undergrads, and then what about grad students? Grad students, and then I'm guessing most over here, faculty, industry. Okay. All right, so I think the presentation today will hopefully excite undergrads about grad school. Hopefully it'll also be interesting to the faculty, seeing the kind of work that I've done, as well as those from industry, and seeing the types of things that the places where machine learning and computer vision are being used in different industrial applications. My talk today will primarily be focused specifically on fingerprint recognition. I do have a slight aside on palm print recognition, where I worked at Amazon for about 1.5 years, so I'll just touch on that briefly. But the content of my talk today will primarily be focused on fingerprints, my PhD thesis specifically, since I have a number of NDAs in place for my work in industry. I don't think there's anything else I wanted to say as a way of introduction. I guess I'll just get started then just with what are fingerprints. I think we're all quite familiar with the concept, perhaps from some science fiction show we've seen, or just looking at the tips of your own fingers. They're just small, beautiful patterns, often called friction ridges, interwoven terminations where ridges stop, and bifurcations where ridges break apart about the size of a US postage stamp, unique to each and every one of us. Just to get you a little more familiar with fingerprints, the first thing to know about fingerprints is there's many different types of them. So that's something that adds to the challenge of fingerprint recognition. If you have one type of fingerprint that you were to capture at an enrollment refers to the time where you first go to give your fingerprints. And then when you come back later, you use a different way to capture that fingerprint. There's different textural characteristics, different degrees of freedom that can be present that make comparing these two things more challenging. So as a way of introduction, these are some of the more common types of fingerprints, starting with here in the top. This is what's known as a fingerprint card. So this is commonly what used to be captured at police stations when a criminal was booked. You'd have your fingerprints inked, and then you'd capture, first of all, rolled fingerprints, or sometimes they're referred to as nail to nail. So these fingerprints, you ink your entire finger, and then you start from one nail and you roll all the way to the other nail. So you capture the entire friction ridge of the finger, hence the name nail to nail, hence the name rolled. The other type of fingerprints that are very common are called as slat fingerprints, sometimes also known as plain fingerprints. And so as the name indicates, you just ink your fingers and you slap them down on the 10-grit card. Typically, slat fingerprints are going to be more hard to match due to the smaller contact surface of the fingerprint and just a little bit less constrained in terms of orientation. Another interesting thing about fingerprints is that they can be somewhat neatly categorized into 5 main types of categories. You have your whorl type, right loop, left loop, arch, and tented arch. So all fingerprints can be roughly categorized into one of these 5 bins. There is some ambiguity there, but for the most part, this is the case. And the names kind of just are self-descriptive. The final type of fingerprint that's important, I won't talk about too much today, but it's something I'm actively working on right now at rank 1, are known as latent prints. So these are fingerprints that probably most of us are familiar with from our perhaps seeing forensic shows, things like that, where a fingerprint is left behind at a crime scene on some surface, some complex background. It's a very smudgy print usually. It's usually very heavily distorted due to the elasticity of our human skin. And so these are very, very challenging prints to match. And so typically you lift that fingerprint using different techniques, digitize it, and then you're going to send it to a database to compare it against millions of fingerprints to basically pose the question of who is this, to try to find suspects for this crime. So now that we know roughly the different types of fingerprints, I want to talk about how are these fingerprints traditionally compared, just at a very high level. And so the first thing that you have to do, for those that are familiar with machine learning, when you are trying to recognize something or you're trying to classify something, you need to extract features from your data points. Another way instead of feature set, you might also say a representation. So a representation of a fingerprint, or it's sometimes also referred to as a template. So I might use these terms interchangeably, but I'll try to be consistent with representation. So for a fingerprint, we start out with the raw pixels. This is a rolled fingerprint from a publicly available data set from NIST. And the first level of features that we're going to extract are more global features, also categorized as level 1 features. There's 3 main types of level 1 features. First of all, you have the ridge flow, indicated by these white tick marks. This is also known as the orientation field. So for every block in the fingerprint, every block of pixels, maybe 16 by 16 window, you're trying to figure out what's the average orientation of the ridge in that block. You also have singularity points, which there's 2 types. One are deltas, indicated by the blue triangles, and one are cores, indicated by the red circles. So deltas, again, are somewhat obvious by the name, but basically where the ridge pattern forms a delta or a triangular shape. And cores are basically points of maximum curvature in the fingerprint, typically located in the center. Some fingerprints don't have any cores. So a tented arch, for example, will not have any cores, which adds challenges when you want to do things like alignment. You maybe need a reference point to basically pin that fingerprint and then align it. With a tented arch or an arch, you don't have that necessarily. Okay, so those were level 1 features. The more common features that are very, very important for the rest of this talk are what are known as minutia points. So minutia points, you could say, are the most prevalent features used in fingerprint recognition today to perform matching. There are 2 types of minutia points. They are more local in nature than all the level 1 features I mentioned before. The 2 types are bifurcations and terminations. So a termination, or an ending, it's also called as, are where the ridge flow is moving along and all of a sudden it stops. So here's an example of a termination here. So you would mark the XY coordinate on this. You can consider the axes X, Y, you mark the XY rotation of the minutia point, and also you have a tick mark here, which shows the orientation of the ridges at that specific point. So you would scan across the entire image and you would get all of those minutia points. And this would form a variable length set of features, which is your representation. And then the final level of features, these are typically not used for matching. They can be. The reason they're not typically used is because they're not usually very reliable to extract. And also you need some more expensive scanners in order to even get the resolution you need to pick up these features. But one very common one are fingerprint sweat pores. So the ridges on your fingers actually have pores that sweat, and you can see those indicated here. So if you can extract those are potentially discriminative features that you can use to bolster your matching performance. And the second are known as incipient ridges. So these are just smaller ridges in between two dominant ridges. So you can, again, extract those additional features, but typically not used due to the computational expense, the unreliability of them, etc. So we're just going to talk from the point of minutia. Once we've extracted those minutia points, we're going to use a graph matching algorithm to compare them. So you can think of a minutia set on one fingerprint, say the enrolled fingerprint, as I mentioned, the first one you capture, as a graph. And you can think of minutia points on the second as another graph, and you're comparing these two graphs. And doing these graph matching techniques, you establish a number of correspondences. So which minutia corresponds to the minutia on the other one. And if we have enough correspondences, then our similarity score, as we get more and more correspondences, and we're confident in those correspondences, our similarity score increases. If our similarity score is above some pre-tuned threshold, then we say this is a match. If not, it's a non-match. So now you have a high level idea of what fingerprints are and how we match them. The next question maybe that you have in mind is why fingerprints instead of, say, another biometric modality? Why have fingerprints become so pervasive in our day-to-day lives, whether it be on our smartphones, whether it be in access control? We've known about them for a long time. I would say there's several reasons for that. First of all, these are very, very established. This is a very, very established biometric trait. Much of the advances in face recognition are much newer. And because it's so established, the accuracy has become very, very good. So these are several academic benchmarks that are currently going on. There's a university in Europe that will basically field submissions from different competitors. So universities or industry alike can submit their fingerprint matching algorithm to a benchmark data set. And then this university will tell you how well you do. And you can see that the best algorithms are performing at nearly 100% true accept rate. So that means that 99.98% of the people that are supposed to be matched are matched, and only 1/10,000th of the people that are not supposed to be matched are matched. So these two errors are always exist in a trade-off. If you just accept everything, your false accept rate would be 100%. So would your true accept rate. So ideally, basically what happens is that as you reduce this false accept rate more and more, this becomes harder and harder to maintain at a high level. As you can see here, at a very strict false accept rate, we're still getting very high matching accuracy with these algorithms, even on very challenging examples. So you can see on the hard subset, we're still at 99.4%. On examples like this, where the fingerprint was incredibly moist, possibly due to the environmental conditions, could have been very humid. Person could have been exercising, who knows, but you can see the fingerprint is very saturated in between the ridges and valleys due to the moisture. So aside from the accuracy, I would say the second reason why fingerprints are so prevalent and widely used as a biometric trait, why they're the most popular, are due to several central tenets which have been established statistically. Those are, you could say, as individuality and also persistence. So there have been statistical models developed which show that the probability that two random people having the same fingerprint is infinitesimally small. For a long time, this was just assumed, and it's not something that's good to assume when you're, for example, convicting people to go to prison based on the assumption that this is true. So there's now very strong statistical evidence that two fingerprints, that the individuality of the fingerprints is a central tenet that holds. And the same is true of persistence. It had long been assumed that our fingerprints don't change over time. Again, there's been statistical models developed that show that our fingerprint patterns do in fact stay the same over a period of at least 15 years. There are some caveats to that. If, like, for example, I've worked in infant fingerprinting, so infants have very small fingerprints. Those fingerprints will grow over time in size, the scale will change, but the actual pattern, the relative positions of those minutia points will not change. And we actually show that in one of our works. So finally, because of these central tenets, because of this high accuracy, fingerprints, as we know, have just exploded into many different areas of our lives, whether it's mobile authentication, whether it's border crossings, whether it's the well-known use case of forensics, The key thing I want to highlight here is that fingerprint recognition can operate in two modes. One is one-to-one matching, also sometimes called verification, also sometimes called authentication. So in a one-to-one matching scenario, I'm basically making a claim of what my identity is. I'm saying I'm Josh, and I'm asking the system to verify the authenticity of that claim. In a one-to-N matching scenario, I'm basically presenting my biometric, and then I'm asking the system, who is this? I'm making no specific claims about who I am. I'm saying, who is this? System then compares against N people in the gallery, tells me who I am. This is also often referred to as search. So verification versus search. The largest biometric system in the world is India's Aadhaar system. Actually, during the PhD, I traveled back and forth to India quite a bit on a different project I was working on and had an opportunity to work with some of the engineers on Aadhaar. So it was pretty exciting talking to them about some of the challenges that they face as engineers working with a database of 1.3 billion people. And for that, they enroll the face, the fingerprint, and the iris, and need to do what's known as deduplication. So that's where you have to, that's like a search scenario. So I would submit my fingerprint and it has to scan the entire database to make sure that I'm not already in there prior to enrolling me in the database. And this system is then used by the government for a number of things, financial services, benefits distribution, etc. Okay, so I think at the beginning, you may be thinking now, fingerprints, there's established techniques, they're everywhere in our lives. Why are we studying fingerprints? And in fact, many people in the computer vision community, if you submit to the conferences, will ask the same thing. They say, fingerprints are everywhere. This must be a solved problem. And that's why many people shifted to wanting to work on face recognition in recent years. However, my PhD advisor and I were able to show that there's a number of problems that aren't solved in fingerprint recognition, especially in different niche areas. And so I'm going to briefly, at a 90-mile-an-hour pace, kind of go through each of those different problems that we worked, well, not each of them, but a number of those different problems that we worked on. The first one is a security vulnerability that we noted with fingerprint sensors in particular. What had been shown before is that you can actually create a fake copy of a person's fingerprint, and then you can use that to hack into a mobile phone, for example. Most of the examples that showed that would first have a person use what's known as a cooperative method. So they would have a person place their finger in, say, some dental molding material to get a very high quality impression of the finger. Then they would cast what's known as a spoof or a target or a phantom from that mold, and then show that they could hack into the iPhone. We developed a process that is uncooperative. So if someone were, for example, to leave their iPhone laying on the table, we can lift a fingerprint from the iPhone, we can digitize it. We have an algorithm that maps that fingerprint from 2D to a three-dimensional finger surface. Then we can 3D print that as a mold. We can take the inverse of it, 3D print it, and then we can cast the target, and then we can break into the system. So further showing the weakness of the fingerprint recognition system to hackers, even when the victim is uncooperative and not providing their fingerprint directly. So our work here was actually picked up by Seeker Media and ended up getting 1 million views on Facebook, which is pretty exciting. Anytime someone's checking out your research, that's an exciting thing. So I just wanted to quick show that I think they did a nice job kind of summarizing the focus of our research. So I'm just going to quick play that a minute for you. Oh, there's no sound. Anyway, there's sound, but yeah, I'll just let you watch the video without the sound. You can see here the high resolution 3D printer to print the molds. These are the casted targets at the end.
What are the molds made out of?
ABS. Yeah. This is a conductive silicone. And here's some images captured by our, so the sensor would capture our target. Here's an example of a contactless optical sensor. So a point this video is bringing up is that there's many different types of technologies used to actually sense the fingers. So an important component of making a spoof, why we call it universal, is that we wanted to show that it could work on all types of fingerprint sensors. So in order for that to happen, the spoof had to have good mechanical properties so that the ridges don't just collapse when you press it on a contact-based sensor versus a contactless. It had to have similar capacitive properties, so it could be imaged by a solid-state or capacitive sensor, such as those embedded on our smartphones. And it had to have the right optical properties in order to function on optical based fingerprint scanners, like the ones you saw in the video here.
Why do you have to make 3D model?
Why 3D model? To make the mold. So if you don't make the mold, then you'd have to have someone provide the mold, I think. So this slide here is illustrating what I just mentioned. There's different ways of capturing fingerprints. There's optical and capacitive scanners. There's contact-based methods. There's contactless. Our target worked across all of these, as you can see the different images produced by our target here. This just kind of describes our target fabrication process that I already described to you. We had an algorithm to map a 2D image to a 3D fingerprint surface, high resolution 3D printing. We worked with the material science folks to find a material that would simultaneously possess all of the characteristics we needed in terms of the mechanical properties, optical properties, capacitance properties. And then finally, once the materials are casted, you extract your finished target. So it was a very interdisciplinary project. So that was kind of exciting. It was my first research project in the PhD. We ended up publishing this to IEEE TIFFs. Got to work with computer science techniques and this 2D to 3D mapping. Got to work with mechanical engineering folks with the 3D printing aspects of it. Got to work with material science folks on the material science components of it. So it was an exciting project. This here shows the 3D targets under a high resolution optical microscope. So you can see here the mold. We were able to measure the fidelity of our ridge patterns on the mold this way, as well as on the target. Here you can see just circular sine gratings that I mapped to a target here so that we could verify the fidelity of our target. Also, we verified fidelity with a number of different tools. So here you can see me using a target to gain access into our lab. So we actually, sort of biometrics lab, had a biometric sensor to get into the lab. And this is us using that to break the system there. So we had the MSU media team come down there to take a video. Another cool thing about this is that IARPA so this is an agency of the government, Intelligence Advanced Research Projects Administration. They fund a number of different projects related to national security. They started this project called ODIN. So ODIN was a program directed at making sure that we could develop biometric systems which could detect if what was being presented to the sensor was bona fide or if it was spoof. They did that for the face modality, for the fingerprint modality, and for the iris. So they funded a bunch of different competitors, consortium of competitors, and each competitive team would have multiple academic and industrial partners. So our specific team worked together with Clarkson University and a couple of other industrial vendors, and we competed against teams from USC, Stanford Research Institute, a couple others I can't remember off the top of my head, but we were part of the Thor team, so we were defending the systems, and then on the other side they had a Loki team, which was basically trying to make these spoofs and then break our systems in this sort of cat and mouse game. So over time, the Thor team got stronger and stronger, but the Loki team also got stronger and stronger as they learned about our systems. And they were allowed to know how all our systems were working. We weren't really allowed to know anything that they were doing. So that added to some of the challenges of it. So that leads me to my next slide, which is once I got started on the IARPA ODIN program, I was trying to develop a fingerprint sensor which could detect if the fingerprint placed on the scanner was a real or a spoof. So initially we're showing this as a problem. We're motivating need for more research for it. Now we're working on the other side of it is how do we actually defend against these attacks? So the way that I did that is with this sensor that I call a Raspberry Reader, because I used a Raspberry Pi single board computer as the processor. The specific difference in my sensor versus those that you would buy commercially is that I use two cameras to capture the image of the fingerprint instead of one. So typically an optical scanner would mount a camera at a specific angle to a glass prism. And in doing so, it would capture what's called a frustrated total internal reflection image, as is shown here. Basically, by mounting a camera at a certain angle to a prism, light from the ridges will reflect back to the camera, but light from the valleys will not. And so that's why you see this very high contrast image that we're all familiar with when we think about fingerprints, where you can see the light being reflected from the ridges, but not the valleys. This image then is still in RGB. It would typically be processed. So there'd be some perspective deformation that would be corrected, converted to grayscale, maybe contrast enhanced, things like that for better matching performance. We added an additional camera. So this camera right here, you could think of as same old as the legacy scanners. We added an additional camera to capture a direct view image, which by mounting the camera at a slightly different angle to the prism, we get light reflected back from both the ridges and the valleys. So you can see a very colorful image of the artifact. finger or spoof being placed on the platen. And a cool thing about the direct view image is it captures a really interesting phenomenon called blanching, which is as you press on your fingertip, you will see a radial diffusion of the blood away from the point of contact. And so that's actually something that you can observe from the direct view image, which would be very hard to replicate in a spoof. So the idea then is using both of these images, one which has a lot more color information, perhaps that can better help us now build algorithms on top of these different complementary image streams to detect spoofs. We open sourced our fingerprint sensor on GitHub, as well as a DIY video on YouTube, so that other researchers can try to replicate this work again. So this kind of gives an example to what I was describing. This is a little bit more of a good illustration of that. So you can see here one acquisition of a live finger on the Raspberry reader. Here's that direct view image, and here's the FTIR image here. Now, if you were to take a spoof, you're going to see the acquisition here. And if you process those FTIR images like a commercial sensor would do, you can see there's a live here and a spoof here. These are virtually impossible to tell which one's a live and which one's a spoof. It's very difficult to tell after all of that processing. But if we look at the raw direct view images, we can see pretty easily which one is a live and which one is a spoof, at least qualitatively speaking as humans, once we've looked at a few of them. And so the intuition is that if we as humans can now more easily tell the difference, perhaps we can train algorithms also to do a better job at this than trying to train an algorithm on this data as input. And so that's what we did. We have three deep networks, convolutional neural networks. Each one of them takes as input a different image channel. So the first network takes as input the RGB direct view, not RGB. We converted RGB to HSV, another color space. That's input one. The second is the raw FTIR image. And the third is the raw FTIR image after it's been processed, similar to how a commercial sensor would process it. And so in the first model, we pass the entire image to get a score for the direct view image. The second model takes individual patches from the FTIR image. And these patches are basically centered and aligned based on minutia points. So you can see at the center of these patches, there's a minutia point. That's how we selected different patches, thinking that minutia points would be harder for a hacker to replicate well. And then the third channel does the same thing with these minutia centered patches, although processed instead of raw. So then we get a bunch of patch scores from the second model, which we average together to get a score for the raw FTIR model. We get a bunch of patch scores for the third, do the same. And then the final score is a weighted average of the three, where these weights are tuned on a validation set. And so then what we showed in the different, basically what we would do, IARPA would host a competition. So all the competitors would go out to Johns Hopkins Applied Physics Lab. We'd set up our shop there, and they would have hundreds of people come through. And they would all present their live fingers, their face, their iris. And every once in a while, a member of the Loki team would come through and place a spoof. And they had a way of knowing what the ground truth was. So then at the end of several weeks, we would tally up the results to see how many spoofs we successfully defended against. So you can see the Raspberry reader in the first task defended against 99.18% of them, and so on and so forth for the different tests that happened over the course of several years. We were consistently one of the top performers in the Odin program. We were the final team left standing at the end, which was exciting given how strong some of the other competitors were. But it was a very challenging project at the same time. We worked very hard on it. It was a large team effort. A lot of time spent collecting data, training algorithms, all kinds of work involved in this project, but had a good result. Oh, as I mentioned earlier, the performance did drop slightly over time because the Loki team was getting stronger and stronger, and we could see, at least qualitatively speaking, the spoofs were getting much better over time. Another aspect I wanted to mention about spoof detection, because I think it's actually a problem with machine learning and computer vision in general, is this generalization challenge. In spoof detection, we specifically refer to it as the material generalization problem. So if you fabricate spoofs out of, say, the materials for the top two rows, and then you were to image them on your sensor, and then you were to train an algorithm to call them spoof, a hacker could obviously come along and make a spoof out of one of these materials. And these materials have different mechanical and optical and capacitive properties. And so when you image them on your sensor, they're going to look slightly different than images that were derived from one of these materials. And so your machine learning model may break. And this is actually a common problem with many machine learning models that we're always trying to fight, is make our models more generalizable to things that we haven't seen during training. With spoof detection, it's a big one because you could think of it as, instead of a binary problem of live versus spoof, it's really an open set problem. We don't know how many spoof types there are. So that motivated us to look at this problem a little bit differently, which is, instead of how researchers typically tackle this problem as a binary classification problem, live versus spoof, we wanted to look at this as a one-class classification problem. So instead of saying, here's all of your spoofs, here's all of your lives, learn some nonlinear decision boundary between them that's very complex, let's instead learn just look at our live data. So we'll train the model by just showing it live data. We'll never show it examples of spoofs. And we'll train the model to learn really, really well what constitutes a live sample. We'll learn a really tight boundary around the live samples, hoping that, if there's some hypersphere around those live samples, then we can discard any type of spoofs that may lie on different sides of the hypersphere. So that's the idea of this here. We actually won best paper from this idea at the International Conference on Biometrics in Greece in 2019.
So the idea is that if somebody is right, there's only one way of being right, because you're right. But there are so many ways of being wrong.
Right.
So that's
Exactly.
better.
Yeah. So we had tons and tons of live data, especially from the IARPA competition, because as so many people come through. So we felt we could really, really leverage all of that live data to learn a very good decision boundary around the live samples. And it takes a lot of work to try to conceive of many types of spoofs, generate new spoofs, image more
Colors
spoof data.
keep coming in.
It's endless. So this kind of here just shows a little bit visually what our one-class classifier was doing. So you can see here the live samples, and you can see the spoofs kind of forming around the peripheral boundary. And what we found was that the one-class classifier was very good at spoofs which were very anomalous, which doesn't actually, that seems intuitive to me. So, for example, if you train a binary classifier to tell the difference between this live finger here and this spoof here, it's probably learning features much different than trying to classify the live finger here versus a green Play-Doh spoof here. So it would fail to classify the green Play-Doh spoof because it's looking for different features that are subtle between these two here. But the one-class classifier can easily bat away the Play-Doh and the gold finger because they're so anomalous from what is a live finger. So we can actually leverage strengths from both the two-class approach for these more subtle cases, and we can leverage the anomaly detection approach or the one-class classifier for these very anomalous cases.
Josh, can you reiterate what your model embedding is and how you're projecting the spoofs onto the live model embedding?
Yeah, so the model we used here would be, we used these 3 GANs. So basically the idea is that a discriminator is technically learning the distribution of the training data. So you pass a random Z into the generator, a random feature vector. The generator generates what it thinks a live sample should look like. And then the discriminator is fed whatever your generator generated as a live sample. And it's also fed a real live sample. So the discriminator's job is to say, is the generator doing a good job at making things that look like live fingerprints? So over time, the discriminator has to learn what a real live fingerprint looks like so that it can tell if your generator is doing a good job or not. So we did that for the 3 different outputs of the Raspberry reader. So you have 3 discriminators, which all have different ideas of what a live image looks like. Each of these has a feature vector at the end, which it's using to classify, is this a real live or is this a synthetic live? And so that's our embedding, which I was showing on the next slide.
But you said you were trying to do this without actually feeding it into spoofs explicitly.
Yeah, so there's no spoofs fed here. The only data that we're pulling from here are live samples, so real live samples.
So how is this again if you're only training the one side of the model?
So we're training both sides of the model. So you're training the generator and the discriminator. So the generator is receiving the random Z, producing the synthetic live, and the discriminator is differentiating between the synthetic live and the real live. You can talk more about it offline if you want, but yeah, it is only being trained on the live data. Okay, so I'm going to put a pause there on the security side of fingerprints, at least from the sensing perspective, and now talk a little bit more about the limitations of the matching process itself. So this work here is actually one I'm most excited about for my PhD because it has significant real world value. We were actually able to license this technology to NEC North America, which is actually one of my competitors now. So the basic idea is, as I said earlier in the beginning of this slideshow, was that when we're comparing fingerprints, we locate these key points known as minutia points, and then we use a graph matching algorithm to establish correspondences between them. So one fundamental flaw with this approach is that our feature set is of variable length. In this case, I found 22 minutia. In this case, I found 28 minutia, even though these are the fingerprint from the same identity. So even fingerprints from the same identity can have a variable length feature set. Because they're a variable length, we can't use simple distance metrics to compare how similar they are. We can't compute the Euclidean distance, for example, between these two sets. Typically, as I said, graph matching algorithms will be used to establish these correspondences, which are fine, but they're accurate, but they're computationally expensive. And as you can imagine, the downstream effects of that, if you're running India's Aadhaar system and you have to compare to 1 billion fingerprints, that computational complexity adds up significantly. And there's another limitation when it comes to encrypted matching, which I'll briefly touch on as well. So what we thought is, instead of extracting a variable length minutia set from the fingerprints to do matching, we'll extract a fixed length feature vector. So the input is just a fingerprint image. We'll just say we have a black box CNN for now, and it's going to always extract 192 dimensional features, which you can think of as a compact representation of what that fingerprint is. Another way that I like to think about it is it's just a point in a high dimensional space. So in this case, 192 dimensional point in 192 dimensional space. We can only visualize 3D, so we'll just talk in terms of 3D. So I extract my first embedding vector. Here's my point. My probe image comes along. I extract the embedding vector again, and if my algorithm is working properly, that point should fall in a very close space in that high dimensional space. So now, if I want to match them, I can just compute the Euclidean distance between them. Or I can also compute other distance metrics. In our case, we're computing the cosine distance between them. And if you have two normalized feature vectors, the cosine distance reduces to d multiplications. You're just doing d element-wise multiplications and d minus 1 additions to get the similarity score. So as you can imagine, if we just have to do d multiplications, d minus 1 additions, the comparison time is extremely fast. Before I show quantitatively some of the advantages of that, I just want to mention that the previous slide I presented, the CNN is just a black box. Of course, that needs to be trained. The job of the CNN is ultimately to learn two very important things that we talk about in pattern recognition. One is the interclass variance, and the other is the intraclass variance, inter and intra. So the model, in other words, needs to know, how can I make sure that two identities are very well separated? How do I maximize the separation between two different identities? And how do I bring together two impressions from the same identity? That would be the intraclass variance that we want to minimize. So we're maximizing the interclass variance, minimizing the intraclass variance. That's essentially the job of the model. There's a lot of details involved in that. But in order to learn that, we need to have both many subjects. That's going to help it learn that interclass variance, what makes people different, what makes fingerprints different. And we also need to have many impressions per finger, so it can learn the intraclass variance. As you can imagine, there's not large-scale public data sets of fingerprints available. So I think that was a hindrance to doing this kind of work for a long time. Fortunately, through our collaborations with Michigan State Police, we were able to do this work on a longitudinal database of 1.1 million fingerprints, where we were able to get both depth of the data set in terms of number of subjects and also breadth in terms of samples per subject. This is the specific architecture that we designed. We call it dprint. It has a few main components which I'll touch on. One is it has an alignment module at the beginning, which is just performing an affine transformation on the input fingerprint. So just a translation and rotation to center and rotate it. And then the second is that it has two convolutional networks as sub-branches. So once the fingerprints align, you extract some features with the base network, and then you pass those features to two different branches. So one thing I want to say here is that although we're now using a deep network to extract our feature representation, oftentimes with deep learning, I think we can be too prone to just think that we can throw lots of data at a problem and we just throw lots of data at a problem, we'll train it, and that will solve the problem. And in doing so, we get lazy and we throw away domain knowledge that we have about a problem. So in this specific case, we know that minutiae are very discriminative features. So instead of just brute force training the model, we want to try to guide the model to look at features close to minutia points. So that's what this is right here. We basically had an additional loss term, which tried to regularize the model to tune its weights such that it was looking at features roughly related to minutia. And we showed that through a number of experiments. At the same time, deep learning is very powerful. And we wanted to allow it to explore additional features, and so that's what that top branch is. And then we combine these features together at the end. We had 96 features related to minutia, 96 we're calling textural features. You concatenate them together into a full 190 dimensional feature vector. And we actually were granted a patent on this, and this is the technology that we licensed to NEC.
I just want to go back a slide. You mentioned that you got data from the Michigan State Police Department. Was it just the fingerprint data you received, or was it any other PII that you got from the inmates?
No, just fingerprint data.
Okay.
Yeah.
Hey Josh, does this alignment diagram account for any translation limitation to the variant to orientation of the image? Because it's anchored on the picture or because it's calculation?
Yeah, so are you asking if there's like a reference point or something that we're using to do the alignment, or?
Or is it agnostic to orientation preference?
Yeah, it's basically, there are some constraints. So we built into, so there's a network here that predicts the plausible rotations and translations. So we put a cap on that, on how much of a rotation you could expect. So the network's only able to output rotations plus or minus, I think it's 30 degrees if I remember correctly, because you're not going to place your fingerprint typically like this. It would be very rare. It can happen, but it'd be very rare. Likewise, we don't want to predict translations that are way off the image. But this is actually using, this module right here is actually a separate paper that was introduced by Google called Spatial Transformer Networks. So it's actually an interesting paper because there's no direct supervision to train this localization network. In other words, I don't have any ground truth translation or orientation that I'm providing the model during training time. The way it works is that I pass this model, this image into the localization network. It predicts the affine transformation matrix. It applies it to the image. And then if I'm doing good transformations, the loss function at the end of my network is gonna be able to better identify fingerprints that way. So this is being, the parameters of the localization network are being updated based on the loss function, the identity loss function, not based on any direct supervision of translation orientation.
Josh, is it possible to give an example of a minutia domain knowledge? I mean, is it kind of like, say, in facial, there's an angle between your eyes and the tip of your nose? What do you mean?
Yeah, I think I have some, let me quick go through my backup slides. I think I have something that might illustrate that. So I think this kind of shows it. So in the top row, you have input fingerprint images. And then what we did here is we looked at basically, these are called, basically they're heat maps, activation maps, which show which areas of the input fingerprint the model is most influenced by. There's different algorithms people have proposed for that. The name escapes me right now. But what we did then is we overlaid the different common feature types that I presented at the beginning. So you can see here in this row, these are the activation maps. These are the singularity points. So you can see the model from the texture branch was primarily looking at these more global features. You can see it's more activated around the singularities and cores. And then you can see here on the second row, the minutia branch seemed to be looking at areas where the density of minutia points was higher. So you can see all the minutia points overlaid on top of the fingerprint image. And you can see the activations, it's much more activated in regions where the minutia density is higher. I think that kind of helps show it visually. Of course, it's still like understanding deep networks is always something that people are trying to do more and more. So it still is in essence a black box, but there are some tools that help us speculate that it's looking at minutia related features. And we did some other types of things, like what if we obfuscate the minutia, what happens to the matching scores, things like this to try to draw insights from the model. Okay, so this is the network architecture to extract the representation. As I mentioned, now we can think of these as points in high dimensional space. If we want to compute a match, we just compute the cosine similarity. D multiplications, D minus 1 additions. So you can see an example here of a genuine pair, so they're supposed to match. And you can see the cosine similarity is 0.78. And the imposter pair gives a cosine similarity 0.55. So if your threshold was 0.6, then this would be correctly rejected, this would be correctly accepted. The way that where deep print really comes in to have real world application is when you use it as a two-stage search system. with existing minutia matchers. So what I mean by that is, let's say India's on HAR system, for example. They actually have our deep print model. If they're not using it, but they did some benchmarking of their system with our algorithm. But anyway, let's say you have a gallery of millions or billions of fingerprints. What you can do first is extract deep print representations from all of them and then do a fast approximate KNN search to find the initial K candidates. Let's say K is 500. So in that way, you can use the speed of deep print to very, very quickly go to the database to find the best candidates. And then once you have, say, 500 candidates, then you can re-rank those candidates based on the more computation expensive minutia matching. So in that way, you leverage the speed of deep print and you leverage the accuracy and interpretability of the minutia matching. These are just some results of our matcher in the one-to-one scenario, the authentication scenario I mentioned. So you can see this is a state-of-the-art commercial algorithm. We're actually at rank 1 beating this algorithm now. But at the time, we were behind them on some data sets and we were beating them on some data sets. So on the rolled data sets, those larger areas, they were beating us. On the slap print data sets, we were ahead of them at the time. Here's the two-stage results. So again, using deep print to find the initial candidate list and then re-rank them based on minutia. So you can see here, I think this is the main result to show. So you can see we're basically, if you use the commercial algorithm Berryfinger, the accuracy during search was 98.85, whereas if we use deep print plus the minutia matcher, we got 98.80%, so just slightly lower accuracy, but our search time, instead of being 30 seconds, was only 300 milliseconds. So significantly cut down the amount of time to do that search. Okay, I'll just briefly go through this one here. This is another motivation for that fixed length embedding. This here is an image of a typical biometric recognition system. You input your image to that feature extraction module, or the representation extractor, or the template extractor, or whatever term you're using. You get a template. Templates are stored in the database. When you want to match them, you're fetching templates from the database and you're computing the matching score here. Typically, in a biometric recognition system, the templates in the database will be encrypted, and then when you want to match them, you have to decrypt them to perform the match. Well, if a hacker is sitting in the middle here, and he knows you're fetching the template, he can grab a decrypted template, and he can use that template to actually reconstruct the original biometric sample. So there's algorithms that show that if a template has been, if you have a template, so you have a fingerprint or a face, you can pass it through a generative adversarial network, and you can generate the original fingerprint or the original face, or you can mine other soft attributes like a person's age, gender, etc. So there's motivation to make sure that these templates never become decrypted. So there's an encryption technique called fully homomorphic encryption. What that means is that and what this scheme enables is doing certain operations in the encrypted domain. So you can do encrypted multiplication specifically, and encrypted additions in the encrypted domain. So if we can do only multiplication and additions, we can't do encrypted matching with minutia matching because we need other operators other than just addition and multiplication. But if we have a fixed length feature vector, all we need again are multiplications and additions to do the matching. Therefore, we can use fully homomorphic encryption to protect the templates. And when we do matching, we can match directly in the encrypted domain. So we can do a match for an encrypted domain. If the hacker steals our template, it's an encrypted template, he can't do anything. And fully homomorphic encryption, there's theoretical guarantees of its accuracy. The result will be the exact same as doing the multiplication in the plain text. This here shows the results of that. The only reason there's any change in accuracy is due to some quantization differences, the number of bits that we used when we did the original matching versus the encrypted matching. Okay, so the last thing I want to talk about related to deep networks and fingerprints is this work called PrintScan. We also patent filed this at MSU and licensed it to NEC. So this work right here, it's another one I'm excited about because I think it makes doing this kind of research more open to all of you, everyone else. So the reason that deep learning hasn't been applied very much to fingerprint is because, as I said, there's not large amounts of fingerprint data available. So what if we can generate a synthetic database of fingerprints that can be open so that people can do research in this area? So that's exactly what this does. So typically, again, it would just take a random Z and it would generate a fingerprint. The issue with that is that we can't just have unique fingerprints. We need to also have different impressions of the same finger. And so this process basically breaks the generation process up into 2 steps, where first we generate what we're calling a master print, just this binarized image. And the second stage, we add textures, distortion, etc. So in that way, we can generate many identities by generating many master prints. By taking a master input to the second master print as input to the second stage, we can get many variations of that same fingerprint. Here's an example of that. So we have the same identity all the way across, and you can see different renderings of it, different distortions. And the end goal, as I said, was to be able to train a recognition model on the synthetic data. So if I train a model now on the synthetic data, can I match against real fingerprints? The nail-to-nail data set released by NIST is an example of a database of real fingerprints that's publicly available. If you train a recognition model on just that data, which is quite small, you can see the results are not that great, 73%. But if we combine our synthetic data with the real data, we can bump our performance up to 87%. And I think there's lots of room for improvement there as well. Actually, at Amazon, I worked on a paper with an intern there where we showed some different models and we were getting accuracies of 95% plus there.
Josh, how well does your GAN produce unique fingerprints that have not been accounted for in training?
Yeah, that's
Try
so.
matching the produced fingerprints back to the database.
We did do that, yeah. So we did find some identity leakage. So we filter all of those out before we release the database. Percentage wise, I can't remember, but it was less than 1%. So we use both our, sorry, go ahead.
Were there any artifacts? Sometimes GANs on base produce artifacts that we can visually appreciate. I don't know if there's a way to do that with fingerprints.
It's possible with some hardcore qualitative analysis. I don't know off the top of my head, but it certainly is possible. I know what you're saying. Similar patterns that you see embedded on fingerprints, yeah. Okay, so that brings me to my last work in the PhD I'm going to talk about. This is called Fingerprints for Global Good. So basically, this is the project I mentioned where I traveled back and forth to India over, I think, 4 or 5 times. We were basically trying to see if we can use fingerprint recognition to match children. You say, why would we do that? I think the main reason is for basically benefits distribution in these countries. There's no good way to know who some of these children are if they come to a clinic for care. So you may have a child that ends up getting vaccinated twice, or you may have people that get nutritional supplements twice that are double dipping and other people aren't getting any because we have no way of knowing who someone is if they've received care or not. There's no electronic record of that. So the goal would be to use fingerprint recognition to better facilitate this benefits distribution and also prevent other problems such as human trafficking. Baby swapping is very common in hospitals in developing countries where babies are taken out of a room with a wristband on. Those bands can be switched and then the wrong baby gets back with the wrong mother, things like that. And right now, fingerprint recognition systems don't solve this problem. So we developed this MSU Infant Prints, which is specifically a fingerprint recognition system specifically designed for infant fingerprint recognition. The first step to that is having a fingerprint reader, which is ergonomically designed for infants. So infants, if you're familiar, always clench their fists like this. And so if you're trying to capture their fingerprints, you're trying to fight to open their entire hand and then get their thumb on the fingerprint playpen, which is distressing to the infant and it becomes distressing to the operator. So we wanted to build a sensor which made that process much more easy for the infant and operator alike. And you can see how this is much easier, where the front of this playpen kind of acts just as a scoop to lift up the thumb of the finger and easily capture their fingerprint. The second aspect of the design is that it's very high resolution. So these infant fingerprints are very, very small. So you need, in our case, we used 2000 PPI in order to be able to make out these discriminative minutia features. So then we went back and forth to Agra, India, home of the Taj Mahal, 4 times, and we fingerprinted 315 infants over time. What we were able to determine is that with our system, so here we are fingerprinting infants in our rural clinic there for children, a rural children's hospital. You can see that while a prevailing fingerprint recognition system only gets 52% recognition accuracy, our system was able to get close to 93% if you enrolled an infant at 2 to 3 months and then came back within 3 months later. There's still work to be done, but it's a significant boost forward, which shows that this is potentially feasible to do. Okay, so all of that is work that I did at MSU.
I was gonna have a question on the previous slide. Can you use that data to predict how the fingerprints are gonna be?
Oh, yeah, so, yeah, exactly. We do have some modeling of the growth over time. So predicting what the scaling factor should be over time. That is incorporated into our system here, yeah. Okay, so after MSU, I graduated in May of 2021. I went to Amazon in June of 2021, where I worked for the Amazon One team. Amazon One is a contactless palm print system. And so, I don't know if you know this, but Amazon is getting into the physical store space. Things like Amazon Go, Amazon Fresh. And the team adjacent to us is called JWO, or Just Walk Out. So that team started before us, and basically what they did, they built a product such that you would walk in the store, you would scan your QR code, which would link to your Prime account, and then you can go about and collect all of your items, put them in a tote, and then when you're done, you just walk out, and it knows what you selected, and it will automatically charge your Prime account. Our team then came in and said, we don't need to use a QR code. You just walk up to this gate, as you can see me doing here out the Amazon Go store in Seattle. You scan your palm, it then pulls up your Prime account, and then you collect all of your stuff and you walk out. So it's kind of a cool experience. You avoid the lines. It does feel a little bit weird. It feels like you're stealing when you just grab stuff and then you leave. But was happy with the things we were able to do there. A couple points I have here, I was able to, there was some root causing the researchers were doing on our production system. Failures were coming into different buckets, and researchers would have to manually go through and figure out what was going on. And so through some of my algorithms, I was able to reduce some of that root causing by 90%. And then the second, which I'm most happy about, is that right before I left, I was able to show that my recognition algorithm was able to reduce the production false reject rate by 60%. So you can say a false reject rate in this case means I don't get in the store. I go up there, I try to scan it, says I don't know who you are. So it's very inconvenient for a customer to have that experience. False positive in this case is worse though, because that means that I'm shopping with your credit card. So we have there's a 0 false positive tolerance at Amazon One. Okay, so I was having fun at Amazon, and then Rank One came calling. So Amazon is obviously a very massive company. Rank One is a startup. The founder of Rank One actually did his PhD with my PhD advisor. And they founded this company, I believe, 7 years ago. The primary motivation for them starting this company was that the United States today uses lots and lots of biometric recognition services, and those are not developed in the United States. So Rank One as a company is trying to have biometric solutions which are completely developed in America and that are as accurate, or eventually we will be more accurate than all of these systems. So this appealed to me, coming in and trying to really at Amazon, you're just one small piece of a big puzzle. But at Rank One, there was an opportunity to really build up fingerprint from the ground up. So historically, Rank One has been a face recognition company. That's their bread and butter, and that's still our primary bread and butter. But Brendan reached out to me and asked me if I'd be interested, given my experience, to come in and build this fingerprint division up from the ground up. So joined them back in September, and we submitted our first algorithm to NIST. NIST is the National Institute of Standards and Technology. So they have a biometrics group at NIST, which companies can submit algorithms to, and then NIST will evaluate them and rank them based on accuracy, based on efficiency, template size, template matching speed, etc. So you can see here by this graph that our results came back from NIST very positively. So you can see Rank One computing down here in the corner, the little American flag. We have the lowest average error rate. So you want to be in the bottom corner. It means you have the lowest error rate and you have the fastest or the least amount of time to compare two templates. So you could say IDEMIA is probably our biggest competitor based out of France. So this is currently, you could say, is probably the #1 biometrics provider. I don't know if it's correct to say in the US, but I would guess so. This neurotechnology, this is very finger that I was showing earlier. So you can see that they're quite accurate, but they're very slow. And then there's only 2 other US solutions, one here, which is not very accurate. Yeah, neither are very accurate, and one is also very slow. So we've really boosted the US ahead on the fingerprint side of things. This kind of just gives a more granular view of the accuracy. So you can see that if you take all the accuracy metrics together and you average them, we have the lowest average accuracy, the lowest error rate of all the different solutions that have been submitted. And then likewise, like Rahat was saying earlier, we are orders of magnitude better on our template comparison time. So this is actually logarithmic scale. So you can see that, you know, even if this was just a linear scale, we'd be doing quite a bit better, but based on the logarithmic scale, you can see we're orders of magnitude better than the competition when comparing two templates. So, my time's almost up, so I'll just sort of summarize. Over the past 7 years, since I graduated from Grand Valley, I've primarily worked on developing fingerprint with a small time away on palms systems, which are more robust via these targets to test the systems, more secure with these spoof detection algorithms and template protection. They're faster with these fixed length representations, which can be compared with cosine distance metrics and in the encrypted domain, which are less biased because they can be extended to all ages now, and also which are more open via the sensor we open source and also this data set of synthetic fingerprints. So all that to say that although fingerprint is widely prevalent and we've all used it for a long time, there are a number of problems we were able to find and where there's room for improvement. That's it. Any questions? Be happy to take them. Thank you very much for your attention. Appreciate it.
But is 192 the optimal line?
In practice, yes. I don't know about theoretically. In practice, we tried a bunch of different sizes, and that's what the best result we were able to get, balancing both efficiency and also accuracy. But there's some interesting work in the face recognition domain, which tries to prove that out theoretically. How many dimensions do you theoretically need to represent a face?
Have any of your fingerprint algorithms been adaptable to their facial recognition at rank 1?
We do have collaborations together, both face and fingerprint guys, and share ideas. And I'd be careful not to say too much, but yeah, I will say that there's ideas that kind of transport across the two. Paul?
So when in your journey did you really start to feel like this was going to be an area that you were going to be comfortable committing yourself to for the long?
That's a good question. I would say, so I think the third year of my undergrad, talked with a lot of professors, decided that I really wanted to pursue a PhD. I didn't really know what in yet. I had a number of areas that were interesting to me. Took Professor Wolf's machine learning class and really enjoyed machine learning. So I knew I wanted to do a field roughly related to machine learning. Then I learned a little bit about computer vision. I started reading about that. And then when I got accepted to MSU, it turns out that they have an extremely strong biometrics program. So things just kind of lined up that would be a really great opportunity. Dr. Jane, in fact, I have to brag about my advisor, I'm pretty sure is right now the most highly cited computer scientist in the world. So
Yes.
okay, so that was a tremendous opportunity that just opened up. I still tell him, I don't know why you took me in, because I felt very green when I started, and I'm very fortunate that he took a chance on me. And so the rest is kind of history. Once I got to MSU, he said, "What do you want to work on?" I said, "Honestly, I don't know. I'm open to working on just about anything." And at the time, he was primarily focused on face, fingerprint, and a little bit of other general CD problems. But everyone wanted to work on face because face was just seen as this is the unsolved problem right now. This is the attractive problem at all the computer vision conferences. So he asked me if he needed a fingerprint guy. And I was naive and said, sure. So I started working on that, and just more doors kept opening up. So there was a postdoc I sat next to in the lab that was extremely good mentor to me. Still friends with him today. He had been working on fingerprints for already a decade. And so everyone else working in the lab on face meant that I had more access to the postdoc. So that was also a great opportunity that opened up. But yeah, that's the progression of events. I didn't really plan much of it. It just, doors kind of just kept opening.
So when you first started to think PhD, did you foresee yourself teaching and continuing research, or was industry something you were attracted to? And then when did you face the choice of, I want to enter industry?
Yeah, definitely when I first started, it was because I wanted to be a professor. I really liked my time here at Grand Valley. I liked the stuff I saw the professors doing here. And I like to teach, so I thought this is my pathway to go to get there. After spending 5 years in academia, I just think I still was confronted with the choice when I got to the end of my PhD of whether to go into industry or into academia. I was still debating it. But I just felt that I had spent so much time now in academia, 4 years in undergrad, 5 years at the PhD. I love certain aspects about academia, other aspects I don't. So some of it was I thought the grass was greener on the other side of the industry. Some of it was just there's really great opportunities to do research in industry now. So a draw to academia is being able to have freedom on research. Well, you can go into industry now and do research. And that's probably been true for a while. But I saw that through different opportunities that were offered to me to do good research in industry. So that was, I think, a big factor in deciding to try this out, and thinking that if I eventually want to become a professor, I'll have more practical experience to bring back to the classroom. So, Zach?
So you presented a lot of your PhD work. I'm curious where the future's going, if you're still stuck on CNNs or if you're doing cooler things now.
Yeah, so I would say at rank 1 right now, so the results I showed on our algorithm so far are on a 10-print matcher. So that's, I go into a system and I'm a controlled user. I'm trying to give good fingerprints. The next algorithm that we need to develop at rank 1 is a latent fingerprint matcher. So that's a more challenging problem where someone is uncooperatively leaving a smudgy fingerprint on a scene. So we're working right now developing that. We're also working on developing a segmentation algorithm, which is, if I go way back to the beginning here, many legacy databases in law enforcement have these fingerprint cards here, which are really nasty and messy. So in order to match these fingerprints, I need an algorithm that can detect the individual upper phalanges of all these fingerprints. And there's all kinds of challenges there. You have handwriting on the image, you can have ghost prints, which is a partial left behind from a previous, all kinds of challenging stuff that's going. This one's actually pretty clean. So we're developing algorithms to be able to do that correctly. And there's all kinds of other niche problems I'm sure we'll get into. One other one I have worked on in the past I didn't mention was what is known as finger photo matching. So you take your smartphone out, take a picture of your finger, use that for matching. So it has unique challenges too, because you have 6 degrees of freedom on your fingers that you're capturing. But I think there's a lot of interest in that in the fintech space, so we might eventually end up going that route. You know, spoof detection is something we're gonna have to develop. Now, there's another interesting problem, altered fingerprint detection, where people intentionally cut their fingers or burn their fingers or take friction ridge pattern from their foot and put it on their thumbs to try to evade detection. So those are things that there's a lot of interest in being able to detect if something's altered intentionally. There's a whole host of smaller problems, niche problems we'll get into eventually, but in the short term, we're working on latent fingerprint matching. That's our big one right now.
You just said in that response that fintech was interested in the technology.
Yeah.
Could you expand on that?
Yeah, so basically just for doing authentication for transactions, you know, like if you want to transfer cryptocurrency from one user to another, like first verifying the authenticity of the user, face recognition, fingerprint recognition.
Well, follow up to that. Do you think that if fintech gets involved, there would be malicious purposes used for your technology?
I'm sure there will be, yeah. So we have to always be guarding against that, trying to be prepared for that. You know, with these, that's why we're working on things like spoof detection to make sure that people can't use our system that shouldn't be using our system, these encrypted matching techniques. I think things like that try to prevent those things.
Okay.
Yeah, but there's always gonna be bad actors, always people trying to break the system.
Of course.
Yeah, when the opposite. So how do we, like you said, when you were at Amazon, that you reduce the false detection rate so that you couldn't get in the store.
Yeah.
So what is the problem with the fingerprints? Probably super problem as well. Are there situations where there is no fingerprint or people want this license or something?
Was it a COVID thing? They didn't want to
Oh.
touch?
Are you asking what is the motivation for palm versus fingerprint?
No, I'm just wondering what how large the problem is that fingerprints are not record.
Oh, the false rejects of fingerprints. Yeah, so there are a number of cases where there's false rejects for fingerprints. I have an example here I think can show that. So this is an example of something that can commonly be false rejected. So if someone is sweating a lot and they place their finger, the water between the ridges and valleys obfuscates the minutia points. Another one, people can intentionally do this. You can intentionally distort your fingerprint. When you press it, you could twist your finger and the elasticity of the skin will stretch in a way that the minutia pattern shifts enough that the score would go down. Which by the way is another problem for future work to be able to detect if that's happening intentionally. Yeah, you see sometimes, so in the IARPA evaluations, when people would come through and provide their fingerprints, you see all kinds of ways that people present their fingers, and I've seen people present a fingerprint like this. So you just get the tip of the finger. So you can't match if there's no overlapping features. So yeah, definitely there are still cases where there's false rejects. It's not a perfect system, but yeah, still extremely accurate and reliable for the most part.
So I have one last question, not last, but so I went to see my eye doctor last week, and the doctor gave me very interesting information. Apparently, the retina, like I think in a fingerprint, you have a finite amount of points, right? You mentioned a graph thing, right? I think it's how many points?
Well, there's a variable length number of points in a fingerprint. So on average, depends on if you have a rolled fingerprint or a plain print, but could be, anywhere from 20 to like 150, somewhere in that range. Yeah.
But apparently retinas have a lot. So eye identification is like a perfect right now.
Yeah. So eye identification, I agree, is very accurate. Typically the way that iris recognition works is through what are known as Hamming codes. Well, Hamming codes are a more generic term for just matching bit strings, but iris Hamming codes specifically are iris codes. So the way that works is you just take the iris and you unroll it into a polar coordinate system, and then the texture of this iris has many unique points, as you said. The issue with iris recognition is that it's not very user friendly. So you have to line your eyes up to the thing, and you're accepting that someone's shooting NIR in your eyes, and you're hoping that they're not doing that too intensely and burning your retinas out.
Probably that's not going to go mainstream anytime soon.
Yeah, so that's
because of the user.
And yeah, you need infrared. There was a little bit of hype a while ago, maybe 5 years ago, that iris was going to be the next thing on phones, but it kind of went away. I'm not saying that there's no use case for it, but I don't know that I see it
on a day-to-day basis,
face or fingerprint.
Probably on a day-to-day basis, probably not gonna happen.
Probably not as much, yeah.
Josh, back in the 90s, I was working on a project where we were using voice authentication. Where is that a thing right now?
Yeah. So there were some guys at MSU working on speaker recognition. There were several ways to do that. So there's prior to deep learning and after deep learning. Before deep learning, I would say the recognition was quite poor, and it was pretty easy to impersonate. So we actually, in one of our machine learning courses, developed an algorithm that could impersonate our professor. And the matcher would say that we were our professor. Post deep learning, the accuracy has improved tremendously, but still nowhere close to fingerprint or face. And there's all kinds of challenges there with background noise and things like that.
That's maybe something a more multimodal type.
I think so. Yeah, I think so. Or like maybe like a home system like Alexa, for example, or something like that. Where it's not so mission critical if you have an error.
Actual stuff like who's speaking.
Yeah, exactly. Yeah. Other questions? Yeah.
So is there a specific percentage of the length that needs to be scanned in order you consider like a precise information? For example, like the new tablets now that it's just part of your finger scan.
Yeah.
And it's just like you don't even touch it sometimes.
Yeah.
Still.
I would say that answer again is nuanced in before deep learning and after deep learning. So I would say before deep learning, you would need a sizable portion of the fingerprint and enough minutia points to be able to match it. I would say after deep learning, yeah, like you said, there are applications where you're talking like, maybe 15 pixels wide by 100 pixel portion of a fingerprint, and they can match it based on the textural characteristics the model has learned from fingerprint. I wouldn't think those would be super accurate, for example, for maybe a 1-to-N application where you have to do a large scale search, but probably for authentication, such a system is okay.
So going based on the experience that I have with seeing grocery store transaction logs rolling. And kind of thinking about, okay, what unique features of a palm are there?
Yeah.
How does, I guess, what's the use case or kind of future for Amazon's kind of contactless palm reading grocery stores in the future? Because I mean, I can see customers waiting outside, probably lined up like it's Black Friday, just to getting groceries if they're using maybe the 1 to N algorithm that they are now.
Yeah.
And maybe it's like the scale of a Myers sized operation or something.
Yeah, that's a good question. So definitely the team is aware of that, and we had discussions, like, the whole thing is designed around making sure that we meet a certain level of throughput. So that means that once a query is submitted, it has to come back within a certain amount of time. The acquisition, you know, like the process for, there's the UI that helps you guide where your palm should be hovered, all of that. There's so much nuance to that, to making sure that when a person walks up, it takes them only, you know, say a second in order to get their thing captured. And it's, what's the amount of, like, how much data can we afford to send? How much can we afford to send back? All these kind of things are taken into the design to make sure that we can maintain a certain level of throughput. But hopefully it would enable faster throughput than people having to wait in line to say, have someone stamp their tickets or something. You know, you already purchased your ticket, you just walk up, scan your palm and walk in, you don't have to have someone sitting there scanning QR codes and stuff like that. So, yeah, thank you.
Anybody else, any questions? Well, thank you, Josh.
Yeah, thank you.